Right. Let's go ahead and talk a little bit more deeply about biodiversity. So, as you went through the simplistic slides on biodiversity, the easy definition is the number of different species in an area. So, if you look at this food web and I asked you what is the biodiversity of this food web, the quick answer might be we just count how many organisms are here. We've got kelp, snails, crustaceans, sea urchins, fish, sea lions, sea otters, and killer whales. So a really simple answer might be 8. The biodiversity of this ecosystem is 8. In all honesty, though, if you were to really look at these numbers, it's more than just counting the different species that you see. For example, this food web could give you two entirely different stories. And what we're focusing on is the abundance, how many of each types of organisms we are seeing in this ecosystem. So if I see this food web, I might assume that it's this beautiful ecosystem teeming with life with lots of fish and kelp and sea urchins and some sea otters, a couple of whales nearby. And I might assume that it's a pretty healthy ecosystem. But in reality, maybe if I looked at the ecosystem, I might see something like this. Right, a desolate barren that has tons of sea urchins. Maybe there's a couple of kelp around. Maybe there was a sea otter that swam through your view and one or two fish. But the majority of the species here are actually sea urchins. So although they might have the same biodiversity number, where we counted the number of species we found, they give us completely and entirely different pictures of how healthy that ecosystem is. So in honors biology, we're going to find a more complete way of calculating biodiversity and give you a better definition for what that word really is, and see how scientists actually do research in the field to actually get a real biodiversity number for an ecosystem. And one of the ways we do this is through creating using this math equation for what's called the Simpson Biodiversity Index. Now, if you were to just search online, you would probably find multiple different ways to calculate biodiversity, but the teachers in Honors Bio think that this is a pretty good one. So we're going to go with this Simpson Biodiversity Index. So how do we measure biodiversity in a community in a scientific study? Well, there's two things that you want to take into account. You want to know what is the species richness. That you should be experts at by now. You just count how many different species did you see, like on my very first slide. We could see that there were clearly 8 species that were identified in that area. Hopefully that's simple for you. But the trickier one then is to look at relative species abundance. In other words, how many individuals of each species are being found? In my first picture of that kelp forest, there seemed to be a pretty even number of species that seemed to have a pretty sustainable way of living for that ecosystem. So there was lots of kelp, there were lots of fish, there were a few sea otters that looked pretty healthy. But sometimes in communities you can have an overabundance of one species that outcompetes everything else and ends up killing off a lot of things. So in our second picture, we saw this kind of desolate barren undersea where it was completely taken over with way too many sea urchins. There's a bigger story going on there that you can watch in a video later. But this one is not so healthy, right? Because we had an overabundance of sea urchins. So a biodiverse community should have a species richness and relatively close species abundances. So you might look at a community here in our town and talk about how many honeysuckle plants there are versus how many goldenrods there are. And that's exactly what we are trying to do with our experiment in honors biology this week. So let's go back and look at the example I gave to you in your notes. If you go to the Google document that you opened up, you were taking your notes early on, the simple definition of biodiversity, and then you got down here to number 7 where it asks you to talk about species richness and abundance. So what I'm going to walk through with you now is how to do this practice calculation here at the bottom of your page. So it's much more difficult than just counting the number of species. In this ecosystem, that number would be 1, 2, 3, 4. There's 4 species in the area. But there's a bigger story going on here. So we're going to use the Simpson's Biodiversity Index calculation. And how you read this up here, we have, well, the researchers have put this in a table that makes it much easier for you to calculate. But this up here is the sum of the number of individuals times the number of individuals minus 1 divided by the total number of individuals times the total number minus 1. And we'll put that in the table so that'll make more sense to you. So here's our table. And let's say we went out to an area and we just started identifying and counting every single plant that we saw. Maybe it was a 3 square meter plot. Okay. And in that plot, as we walked around and we looked, we found bush honeysuckle. We identified it and counted 7 of them. We found 15 different snake root plants. We found 22 goldenrods, those are with the yellow flowers. And we found 9 plants of common ragweed. All right, our in-field study is done. We've counted everything that we saw, we recorded it, we're ready to come home and do our calculations. So the first step in this table, we just put in the first row, our in, the number of each individual species here. We've typed that in for you. The second column is in minus 1. So I'm going to look at my column here, that was my in. 7 minus 1, which is 6. Okay. Now you don't have to type in that minus 1 every time. I'm just doing that to hopefully help you see what I'm doing in my head. So 15 minus 1 equals 14. 22 minus 1 equals 21. 9 minus 1 equals 8. Okay. In the next column, then we're going to take, it says we're going to take in times in minus 1. Well, if you look back, those are the headings of our last 2 columns, right? So here's my in. Here's the answer to n minus 1. So I'm going to take 7 times 6. That equals 42. I'm going to take 15, my in, times 14. That's 210. 22 times 21, 462. And then 9 times 8, which is 72. Okay. Now, down here at the bottom is where this table gets a little bit more confusing. It's not too bad, but it is kind of tricky. So the only time we're going to total our rows here is in this column. These 2 columns, the n minus 1 and n times n minus 1, we're going to do something different with. So what I want you to do next is you're going to add 7 plus 15 plus 22 plus 9. 7 plus 15 plus 22 plus 9. And that's going to equal 53. Okay. Now what you need to do is to run this number through the same equation that you just did. So this is now my n, 53. My n minus 1 is 53 minus 1, which equals 52. Okay. And then 53, my n times n minus 1 is 53 times 52, which is 2,756. Okay. I will say that this row right here is where people make their most common mistake. And that is they accidentally add this number here and this number here, and then they get themselves lost. Okay. So you have to be really careful that you're running this in. This is actually your capital N. You're running this in through the same equation that you ran the others through. So 53 minus 1 is 52. Multiply these together and you get that. I'll put this in here too. 53 times 52, so you can see what I did there. Okay. So then you get your full answer there. Now over here, the last column is your total column. And this is a time when you do want to add your last lowercase n's, not this total down here. So this is also tricky. We're going to add 72, 462, 210, and 42. So everything above that total line gets added in this total section. So 42 plus 210 plus 462 plus 72 equals, and that's going to give you 786. I looked up these, I calculated these with a calculator before I did it. I'm not doing all this in my head. I'm not that quick. And then this bottom box, you can just move over this exact same number if you wish, or you can just leave it blank. But that bottom number we're just going to put, I like moving it over because it makes it easier for me to see what I'm going to do next. 2,756. Okay. So these two numbers become my numerator and denominator in my equation 1 minus the sum of n times n minus 1, which is 786, divided by the sum of the total n times n minus 1, which is 2756, or 2,756. Okay, you can punch that into a calculator and see what you get. All right, I get 1 minus 0.285, which is the same as 0.715. Okay. There's my Simpson's biodiversity index number, 0.715. And again, this is another place where students often make mistakes. They will, on accident, forget to do the 1 minus. So they'll come up with this low number of 2.285, which is a really low biodiversity number. And that does not give an accurate picture of what the actual biodiversity is of the community. So if you find that you've done something wrong, those are the two key places to look. Look at your totals column down here. Make sure that you totaled this column here, and then ran this number 53 through the actual equation, n minus 1 and n times n minus 1. And then also make sure that when you put your numerator and denominator into this 1 minus equation, make sure that you didn't forget the 1 minus piece of that, okay? So the correct Simpson's biodiversity index for this community is 0.715. The closer this number is to 1, the higher the biodiversity is of an ecosystem. So this is, it's a relatively biodiverse community. It's not super high. A good biodiverse community might have 0.9 something or higher. So this one's kind of average. When you calculate, let's say for your project, you're going to have to calculate the biodiversity of 2 areas. So you're going to have to do this table twice, likely with lots more organisms in it. Maybe the other one you calculated was like 0.825. Okay. So now you've got, maybe this was area A, and maybe this was area B. So the type of question you might be asked is, which area has more biodiversity, and how do you know? Well, you could initially say that area B has more biodiversity than area A because the Simpson's value is closer to 1. Okay. Then you would want to go back and look into the actual numbers we gave you for those two different plots. What is it that makes Area B more biodiverse than Area A? Is it that there are a more equal abundance of species? In other words, everything seems to be pretty even in B? Alternatively, that would mean like in A, maybe there's an overabundance of honeysuckle or some other kind of plant that's skewing the numbers. Or is it just in general the total number of species in the area? So you'll have to kind of disseminate that information by looking at the actual data provided to you through those tables. I hope this helps you with calculating Simpson's Biodiversity Index. Send me an email if you have any questions or want another tutorial on how to do this. Thanks, you guys.